All right, let's talk about matrices. A matrix can be thought of as a list of vectors. For instance, matrix A could contain the vectors 1 and 2. In reality, this will look something such as matrix A is equal to 3, 4 and negative 1, 2. 3, 4 is one vector, and the other vector is negative 1, 2. The vectors are along the columns. A matrix has m rows and n columns. For instance, this matrix has 1, 2, 3 rows, so m is 3. Now this matrix also has 1, 2 columns, meaning n is 2. Now, sometimes you will want to talk about specific elements in a matrix. The system for doing this is outlined here, where the first number represents the row and the second number represents the column. So for instance, this element of our matrix, A at 1, 3, is the element in the first row, third column. Or this element here, 2, 1, is in the second row, first column. Now, one of the uses of matrices is representing a linear combination. Let's say we have the vectors 3, 4 and negative 1, 2. We can represent a linear combination of these two vectors this way. The matrix contains our vectors 3, 4 and negative 1, 2. And the vector beside it contains the coefficients or the constants. So what this notation represents is that we have 2 of our first vector, 3, 4, and we're adding 5 of our second vector, negative 1, 2. So the notation on the left is a more concise way of representing our linear combination, where our vectors are stored in the matrix and our constants are stored in a vector. In this case, this linear combination ends up being 118. Of course, we could do this with larger vectors and with more of them. For instance, this matrix contains 3 three-dimensional vectors. And now, of course, we need 3 coefficients, as we need to know how much of the first vector we need, how much of the second vector we need, and how much of the third vector we need in our linear combination. So in this case, we have 3 of our first vector, which was 1, negative 7, 0. We have 8 of our second vector, which was 1, 1, 2. And we have negative 1 of our third vector, which was 4, 5, negative 11. And you could, of course, do this calculation to find what vector is this linear combination ends up as. Sometimes we may want to ask, how much of each of these vectors do we need to combine to get some other vector? So let's take our vectors 3, 4, and negative 1, 2. How much of each of these do we need to produce, as a linear combination, the vector 1, 1? Well, another way of asking this is writing this statement. So we have our vectors 3, 4, and negative 1, 2 in our matrix. And we don't know what our constants are. We don't know what alpha 1 is and alpha 2 is. So we can write that vector as alpha 1, alpha 2. And this is the vector we want to find. We want to know how much of each do we need to combine to get the vector 1, 1. And again, we know that in this notation, it means we have alpha 1 of the 3, 4 vector, and we're adding alpha 2 of the negative 1, 2 vector, and that gives us 1, 1. Now we can multiply each vector by those constants, and it affects each element. So we get 3 alpha 1s, 4 alpha 1s, and we're adding negative 1 alpha 2s and 2 alpha 2s, and that equals 1, 1. Then we can add these together to get 3 alpha 1s minus 1 alpha 2, and 4 alpha 1 plus 2 alpha 2s equals 1, 1. Now this ends up giving us two equations with two different variables. This is a system of equations that we can solve by substitution. So we can rearrange the first equation to be alpha 2 equals 3 alpha 1s minus 1. Then we can sub that into the second equation. We can distribute, combine like terms, and then find that alpha 1 is 3 over 10, which means we need 3 over 10 of our first vector, 3/10 of our first vector. We know alpha 2 is equal to this, so we can sub in our alpha 1 that we just found, and we get that alpha 2 is negative 1 over 10, which means we need negative 1 over 10, or negative 1/10 of our second vector. So if we combine 3/10 of our first vector with negative 1/10 of our second vector, we get the 1, 1 vector.